To solve a basic form of a trigonometric equation, first off, you're going to need good knowledge of the unit circle. Additionally, knowing what is positive and negative in each quadrant will be really helpful to know. So generally speaking, there will be two solutions on the interval from 0 to 2 pi. And the two solutions will be from the two quadrants where the trigonometric function is either positive or negative depending on the given ratio. So look into both quadrants. Where the trigonometric ratio has that sign. For example, if I say solve on the interval from 0 to 2 pi, we'll start off nice and basic. The sine of theta is equal to 1/2. Now, given that we have the sine, and given that it is a positive ratio, that means that we're going to be looking for a quadrant 1 angle and a quadrant 2 angle, where somewhere in those two quadrants, the corresponding y-coordinate on the unit circle is equal to 1/2. If you can identify these two angles, then you have identified the solution on 0 to 2 pi. The quadrant 1 angle where this occurs is pi over 6, and the quadrant 2 angle where this occurs is 5 pi over 6. Now these would be considered the solution on 0 to 2 pi. For the record, if we were interested in a general solution, we'd be talking about these two angles and anything coterminal to these two angles. The way that we create things that are coterminal to a given angle is by adding multiples of a full revolution. In radians, that would be an integer times 2 pi. The integer that we use is described as k. So rather than saying 2 pi times k, we frequently just say 2k pi. Another basic form that will involve good knowledge of the unit circle, I would like to solve on 0 to 2 pi. And I'd like to do the cosine of theta is equal to negative root 2 over 2. Now for this example, we're dealing with the cosine, and the ratio is negative. So in which two quadrants do we find a negative cosine? That would be in quadrant 2 and quadrant 3. And in those two quadrants, there will be a point on the unit circle where the x-coordinate is equal to negative root 2 over 2. The two angles in question, the one in quadrant 2 would be 3 pi over 4, and the one in quadrant 3 would be 5 pi over 4. And if we were to add 2k pi to either of those, we would have a general solution. Next up, once again, we'll solve on the interval from 0 to 2 pi. I'd like to do tangent of theta is equal to the square root of 3. Now, in order for the tangent of theta to be equal to the square root of 3, we'd be looking for an angle in quadrant 1 or an angle in quadrant 3, because that's where the tangent is positive, where the opposite side is root 3 and the adjacent side is 1. Or, in quadrant 3, that would be negative root 3 and negative 1. In order to make those two things happen, we would need to have a hypotenuse of 2, as is hopefully readily identifiable. So really what we're looking for would be an x-coordinate of 1/2 and a y-coordinate of root 3 over 2. Or in quadrant 3, an x-coordinate of negative 1/2 and a y-coordinate of negative root 3 over 2, as that would be the cosine and the sine of these two angles. the angle in question for quadrant 1 would be pi over 3. And the angle in question for quadrant 3 would be 4 pi over 3. And again, adding 2k pi to either of those would still give you a good result. Well, that'd be a general solution. Now let's say, for the sake of argument, that you get something thrown at you that you don't necessarily recognize. Like the cosine of theta is equal to 0.437. Well, that's not something that I recognize from the unit circle. But it's certainly possible that an angle like that could exist. So throwing down our unit circle, 0.437 would be right about here. And we would have something right up here, and we would have something right down here that corresponded to that. So we would have a quadrant 1 angle, or quadrant 4 angle. However, if we know a ratio, we can determine the angle by making use of an inverse cosine. So theta would be equal to the inverse cosine, or arc cosine, of 0.437. But the arc cosine can only give an output that's a quadrant 1 angle if the ratio is positive, or a quadrant 2 angle if it's negative. So this theta right here is going to be the inverse cosine of 0.437. We also want the angle that's in quadrant 4, so we'll need to chase the angle from quadrant 1 into quadrant 4. And the way that we do so is by taking 2 pi minus that angle. So the exact versions of the final answers would be the inverse cosine of 0.437 and 2 pi minus the inverse cosine of 0.437. If so desired, you can use your calculator to approximate. Similarly, if we were dealing with an inverse sine, or the sine of something that we don't necessarily recognize, like sine of theta is equal to 0.819. I'll draw the circle first this time. There we go. So somewhere on the y-axis, we're going to have an angle like this, a corresponding point over here, and a corresponding point over here, and I'd be interested in finding this angle and finding this angle. Now once again, we can make use of an inverse sine and say that theta will be equal to the inverse sine of 0.819. But the inverse sine is only capable of giving us a quadrant 1 or quadrant 4 angle. As a result, this is the angle that you just found. In order to get the corresponding quadrant 2 angle, we would need to chase the angle from quadrant 1 into quadrant 2. And the way that we do so is by saying pi minus the given angle. So this would be theta equals pi minus the inverse sine of 0.819. That would be our two answers. Now last one, and I realize we don't have a lot of space to do so, but we're going to go for it anyway. The sine of theta is equal to 5. The answer to this would be nope. The reason that the answer to this one is nope is due to the fact that the range of the sine function goes from -1 to +1. So if a number has to be between -1 and +1, when is it ever going to be equal to 5? Well, the answer would be nope.